There's not one biomem and two biomems, okay? It's one biomems. It's just an acronym that we use, okay? Micro electromechanical systems, okay? Let's start. We leave the bio. We'll talk enough about bio, but micro means that at least one dimension has to be in the micrometers, okay? And that's the actual challenge related to MEMS design, okay? Because then we're going down to a scale where fabrication processes, you cannot do it with your bare hands. You actually need to use specialized tools to actually get one of the dimensions, if not more, down to the micro scale. Micro scale between 100 nano and 100 microns. There's no clean cut, definition of micron. But more or less, if you tell me that your device is, 10 millimeters, that's not a biomems. But we're actually pushing, I should update that because we're actually pushing 100 nano down to, almost we're going to actual atomic level right now, okay? So that could be 10 nano or something like that. That's state-of-the-art biomems. That's what we're pushing the edge towards even smaller and smaller. Because what we want to do is to actually interact with the smallest possible particles or biomolecules that are present biologically, okay, in our body or in a cell culture, or something like that. So single cell resolution, very accurate resolution, and that's where that scale comes from. Yeah, question. Yeah, it's no, the machine is, yeah. So the machine is actually very big in the foundries or in the fabrication labs. The machines are usually very, very big for scaling also, because you want to make 100,000 of these devices with that level of accuracy, okay, in maybe a week or a month or something like that. So machines are very expensive, and I'm gonna post a note on D2L about the lab facilities that we use to actually make these devices. This is not something that you do, in your home office or home workshop or something like that. You need specialized lab facilities that are clean enough not to disturb the process, okay? Because an air particle or dust particle is in the range of, 1 micro to 10 micro, 100 micro. So if I have dust in the air and I'm trying to fabricate a device that has to have a resolution of 100 micro, just one dust particle is going to prevent that from happening. So I need to clean the space, and that's why we use a clean room. We are very original with names, but the lab is called clean room, okay? And they vary in size, they vary in class, depending on what is the smallest size of the particle that you allow into that room, okay? So you've got class 10, class 100, class 1,000, class 10,000, 100,000. This room is probably class 10,000. After you came in, probably 100,000, but this morning was maybe 10,000 or something like that. So it's something that you couldn't actually fabricate a device, a macro scale device in this space, okay? Electromechanical means we are integrating two different components that we kind of thought about as separate. Yeah, go ahead.
So Professor, when the university students need to manufacture, like a master's student, for example, when they manufacture a device, you send it out to like labs like TSMC, or
yeah,
so you manage in-house?
Yeah, so good question. The question is, master's level applies to all different academic levels or even companies. Do you fabricate these in-house, or do you fabricate these by sending it out to a manufacturer? Both. It really depends on the complexity of the device, because as we'll see already from next week, it's like basically baking a cake, layer by layer, okay? So you build one layer, you carve some structures on that layer, then you build another layer on top, then you carve some more structures, and so on, okay? How many layers do you have? 2 layers are usually manageable. Okay, so you can do it at master's level, for example, PhD level. You can go to the clean room. For example, we have a tiny clean room at TMU. It's not really too useful, but we use the U of T clean room. They have 2 of them. So you can go there and do it yourself. But if you have 16 layers, 25 process steps, and 17 masks, you can't. Okay, so you send it out, and then they, get samples back. But that's a lot more costly. Okay, so for example, to give you an indication, you take a 1 millimeter squared. 1 millimeter squared. It's smaller than this quarter here. This is from this is actually 5 cents, United States. So it's smaller than this. Per square millimeter, we're talking about $5,000. Okay, this is 25 cents. So there's actually a lot of research on low cost biomems. How do you make something useful that can maybe be implanted or wearable, but for a fraction of the cost? Okay, you have to be exotic. You have to use exotic materials, exotic processes. You have to try, to put things together in a way that reduce the cost. Okay. But from an integration point of view, basically we are making 2 different domains talk to each other. Okay, the electrical domain, the mechanical domain. What does it mean? That I have electrical parts within the device, but I also have moving parts. Okay, and that's a fundamental uniqueness of MEMS devices. I do have moving parts. I can have cantilevers, I can have drug delivery systems, pumps, micro pumps, things like this. So if I can control those mechanical parts electrically, then I have the best of both worlds. Okay, then I have a device that I can use to do a lot of different things. Okay, so little by little we'll actually, unfold all the different components and applications. But of course, we talk about single chip. Okay, so from next week we'll start talking about wafers. A wafer is a disk of silicon or glass or something like that. That's where we start actually patterning our devices. Okay, so we start talking about that on next week. But from the wafer, then we dice the wafer into smaller chips that are usually this size. Okay, a little bit bigger, a little bit smaller. Okay, so that is called a chip. Okay, so we talk in terms of biomems chip or microfluidic chip or lab-on chip. Okay, and then that chip has a lot of functions and functionalities that we need for our application. Okay, and you can see some of the applications. Okay, this is by no means comprehensive list of applications. There's more and more coming up because we're uncovering new processes, we're uncovering new materials, we're coming up with new materials from a chemistry point of view. Okay, and we can synthesize novel materials that have nicer properties, like graphene, for example. So this opens up a new range of applications, and then a lot of research pours in those applications. Hey, we can do DNA sequencing in 1 day, and then there's a lot of research going on in that. And actually, thanks to biomems, that's exactly what's happening. DNA sequencing was $100,000 feat 15 years ago. Now it's a couple of $1,000s and going down in price. And they can do it within the week. Okay, before it was months and months. Okay, so that's the kind of stuff that biomems is really making things happen. Okay, and in terms of materials, we stick to silicon, glass, and polymers. Roughly speaking, sometimes they bring in some different types of materials depending on what we're covering. That brings back what I thought about before. We don't have a textbook. Okay. We don't have an actual textbook for this course. Why? Because this field is moving so fast that as soon as they publish a textbook, it's obsolete. I can tell you that, okay? Because it takes a couple of years to publish a book. A couple of years later, there's so many more research papers and so much more research in the field that it's better to stay up, in tune with research rather than, because we're not really dealing with fundamental concepts so much. Okay, those fundamental concepts come from physics, chemistry books, and electrical engineering books and mechanical books, fluidics and things like this. What we want to see is what's happening in this field. Okay, so I'm using a large amount of research papers, and you are free to actually use the same research paper. So every few slides you see a citation somewhere. Okay, some citations are from maybe 8, 9, 10 years ago because it's a very interesting device, but you always can look behind what's beyond that paper, what has happened beyond that paper. So you go and check the paper, you check who cited that paper, what they've done in that specific topic, that specific field. But as you work on your project, you can actually use some of the references that I have in the slides already, okay, as a starting point, okay? It's really difficult to navigate this space right now, the research space right now. There's millions of papers and journals out there, and some of them have a very nice title, but there's nothing behind. So I actually posted a list of reputable sources that I consider from a researcher's point of view, reputable sources. Again, not a comprehensive list, okay, you can go past. But for example, the International Journal of Economics and Biomems doesn't sound to me like, very solid type of journal. But you've got the Nature, journals, you've got the Biosensory Bioelectronics from Elsevier, Sensor and Actuators, also from Elsevier. So there's a couple of reputable sources. Given that you only have a few weeks to work on this project, start from those sources, okay? So you know that your project is going to be more solid, and sometimes you find a source online that is like, who knows where it's coming from, and always ask yourself the question, is this a valid source? Meaning, are they showing the actual device, and are they showing measurements from that device? Then I can trust that source. Okay, you can manipulate measurements, blah blah blah, but let's stick to what we have at our disposal. A lot of times a design, I can sketch a biomems right here, right now. Okay, doesn't mean that it's gonna work. Okay, but it could look amazing. Okay, it could look really something like, wow, this is revolutionary. Oh, small problem, you can't fabricate that. So check that component when you look at papers. Okay, don't just check, oh, this device looks amazing. Have they built it? How does it look like? What materials did they use? What measurements? And how good they look? How good the measurements look? Okay, because I can measure glucose very easily, but with what accuracy do I need to measure glucose? Okay, these are kind of questions that you really want to raise and develop this kind of research attitude at this stage. Okay. Let me see what I have left. Yeah, I have an interesting video. Anyways, this is again going back to the microscale, just to give you an indication. We are between an ant and DNA. That's where we are sitting right now. An ant and DNA. Okay, so 1 millimeter, 10 millimeters, something like that, and DNA strands 2 to 10 nanometers. That's where biomems sit. Okay, in the microscale space. Okay. And you can already see some examples here that I put in there. That MEMS device that is 10 to 100 micrometers, and it's got some mechanical parts to manipulate red blood cells. A red blood cell is about 10 to 15 micrometers in size. So if I want single cell resolution, I need to actually talk the same language. I cannot have a massive device, because otherwise I'm going to end up manipulating several cells at the same time. I want to manipulate a single cell, okay? So I need to make sure that that component is in the range of the size of that cell, okay? And then it goes all the way down to to a DNA processing, DNA sequencing. So we talked about DNA sequencing. So the state-of-the-art technology in DNA sequencing is nanopores, okay? You have little holes that are nanometers in size, because the DNA strand has to flow through the pore. And then I can measure the electrical activity current across the pore, and every little component of the DNA will have a different profile, so I have the signature. Okay, so that's how I extract the signature. But I need to fabricate nanometer holes through, I can pierce this, is 1 millimeter, something like that. So think at the scale of that machinery that you need to actually drill, it's not drilling, of course, but drill, pass me the term, a nanometer hole through a very thin wafer that is like a piece of paper, okay? And thinner than this, okay? So that's the scale of things, and that's the precision of things that we need. But along this line, I don't think the audio is going to work. Doesn't matter, I'll talk over it. What matters is that you see what's going on, okay? So this is someone, I don't know if the audio, I couldn't find the audio jack in here, so I don't know if the audio is going to work, but this is someone in McMaster. They used an ion beam miller, and we see that technology. So you can, it's basically a gun that you use to inject ions, okay? In this case, gallium ions, one ion at a time. And then you focus it into a beam to create structures, okay? So this is what this researcher is going to show, and because it was holiday season at that time where they actually did it, they did a gingerbread house, okay? A miniature, micro-scale gingerbread house. I basically draw your attention to the scale of this gingerbread house. So let's see. I'm going to boost my audio, but okay, so the audio is not going to work. So it's going to show that is going to show the gingerbread house, and these researchers basically saying that they just acquired this multi-million-dollar ion beam. I should have done lip sync or something like that. They acquired this amazing tool, and you basically is an ion beam gun that is manually controlled. Okay, you can control it electronically, but also manually. And basically, you can just control where the beam is at a microscale precision, using also a microscope that has to have the same precision. So you got these two tools into one, and then you start carving structures into silicon. So this is a silicon wafers, a piece of silicon, and then the researchers started carving structure using gallium ions. Okay, and then basically you're gonna see that. Yeah, you're going to see that it's going to zoom out, and the gingerbread house is standing on a snowman that is also carved in the same way, and the snowman is smaller than a human hair. So you can imagine the scale of that gingerbread house. That's the technology that we have available right now. If you have millions of dollars, of course, but we do have that technology, and actually we do have that in a U of T, in the basement of U of T. And it has to be in the basement of U of T, of the Galbraith building at U of T, because of vibrations coming from the subway, okay? They needed to find a space with the least possible vibrations, because when you have that nanometer resolution, even a small vibration is going to shift that beam, okay? So you're not going to have that resolution. So they had to do a survey of U of T and go in with vibrometers everywhere around campus and say, okay, this is the spot, which is like a very dark spot in the basement of an old building. But researchers don't mind that, okay? They mind about the tool, not the space, okay? There was a question, yeah?
So you were saying like some finance devices can't be designed, they can't be fabricated. So what exactly limits them?
The technology that you have. At some point, right now we are dealing with nanometer scale, okay, but you have to have that tool, okay, or you have to pay someone to access that tool. Okay.
Say you have like unlimited resources. Is there anything that like fundamentally can't be designed?
Well, we're close to atomic level here. Okay. So at some point at atomic level, I don't know how you interface with, atoms directly, and fabricate things at that level. I don't know. That's a physics question, and even quantum researchers don't actually fully understand what's going on. So let alone build a machine that actually operates at that scale. But in terms of technology, to be honest, we have a lot. And we have a lot more than we need, particularly in this space, in the biospace, okay? Right now, I think we have a lot more than we need. So we have a few years kind of paved already for us in terms of technology. But that's why it's always nice to see, is there something else coming up? Because, of course, these companies that develop these $1 million devices, they have to keep selling. Okay, so they cannot be like, oh, okay, we're done. There's nothing else. There's always something else. Okay, so they're always studying. But usually it's more like a precision of, for example, I just talked about this vibration, how sensitive you are at this scale to vibration. Some companies are thinking about compensating for that. What if I have a vibrometer integrated in the, and then you kind of adjust, and compensate, yeah. So that kind of stuff, they think about precision right now. So a lot of the companies are actually focused on precision. But to answer your question with another, it's not a video, it's a picture. If it comes up, let's see. Yeah, 1997. This is a nano guitar. Okay, I don't know how many of you play guitars, but you cannot play this because this is in the micrometer scale. So look at the size here, 2 micrometers. So in length is about 20 micrometers or something like that. That's a human hair, not my hair, but your hair. Okay, so we had that technology already in '97. This is '97. Okay. The main problem, not of MEMS, of bio-MEMS, is applications, okay? Because when you bring bio in, and we'll see that, you are dealing with an environment that is not very friendly, okay? So you're using this kind of device, and you interface it to a cell. A cell is not gonna like that. And what happens is that either the cell dies, or the cell culture, the tissue, are going to reject that, okay? So when you're thinking about implantable devices, then you have issues with biocompatibility. And that's the main issue with biomems. And we'll circle back to this when we cover biosensors, because we'll take a look at how can we modify a MEMS device to be a little bit more compatible with the biological medium and body, human body, okay? More often than not, even if you do cell cultures on a petri dish that has some MEMS devices, the cell culture dies within a week because it's not their natural environment, okay? And they're interfacing with something that we don't have silicon or glass in our body, so cells don't understand that. But if you can have an intermediate layer that is like hydrogels, for example, or something that can actually be a little bit more compatible, then cells are not going to care about the silicon that is underneath. They're only going to care about the interface layer. And they're going to say, okay, it feels like a natural environment. I can grow. And that's how you always have to think about these things, okay? Okay, let's maybe take a break now. So it's a 3-hour lecture. Of course, today is going to be shorter. I'm going to take regular breaks, okay? 2 breaks per lecture. So yeah, let's take 10 minutes and then we'll go through applications, okay? Yeah.
You were mentioning something about masks.
Yeah, we'll get back to that next week. We'll start from that next week, yeah. The first thing we're going to see is masks.
I'm excited.
Yeah.
I may not be able to be here of all classes because sometimes, right now, I don't have work today. But if I do have work or something that conflicts and if I can't show up to a lecture, the course is online and I can review those.
Yeah, it's all online and recording the videos. I'm recording lectures.
Thank you so much. And also, you mentioned that you also started group chats for grad students to
Yeah,
talk on,
yeah.
on D2L.
I'll do that on Google. On Google, yeah. So I need to see who's staying on, but then I'll include all your names, and then we start a chat there, so you can actually get to know each other and create groups.
Thank you, Professor, because
Okay.
now I can actually be able to talk, even though if I can't.
I know. Yeah, sure, absolutely. And then after that, once you have a group, then you can go on with your own way of communicating with the group. My suggestion is always spend some time to meet with them, virtually or in person, doesn't matter. But sit with them, talk about the project regularly. Okay, don't wait till week 10.
Actually, right now, I was going to talk with some people here who might be.
Yeah, I have no idea who's postgrad, who's not. I remember some of the faces, but from the exam probably, because we had the exam in person. So. But of course, a lot has happened since then. So it's, but I think it's 16 of you. It's 16 of you. Yeah, so far. Yeah, there were 2 in the back. I think two students in the back were graduate. From here, I don't think. Yeah, but don't worry, you'll meet some other people.
We were all very
Technically, I'm robotics, but I want to do movies, so that's part of the mechatronics program. So that's why one of my supervisory professors says to take this course because it has MEMS in the title and it's used in medical applications. So that's why I'm here.
Not intervention, macro and nano manufacturing.
Krishna, Dr. Krishna. I took that course. It's crazy.
But I mean,
I got a high 7. I did like fantastic on the project paper. But it was terrible on the midterm. My project is so much better than gas. I don't know how I got it. It's gonna speak. I did my undergrad at a different university. It's pretty similar to here. I got my degree actually in electrical engineering. So even though I had electrical, I did robotics, control systems.
There's a right answer.
And I've been told this one's also related to mechatronics.
I'm a French
That's why I'm taking this shit. Right now, I got my grad students so I can work together.
Someone give me the right answer. Huh? I think so.
Okay, not Marion.
No, honestly, you're so right. We should get manicure. I'm down. Let's do it.
Again, I don't know the project details.
Yeah, we'll get the right side.
do you have any background in this?
I have but I do know what matters is. I do know
It was on
I have a degree in
better. It's not off a fresh chunk of butter.
I got my undergrad at Lakehead.
You got eye?
It's a different one, but I know how to use
Yeah, I know. I'm gonna do that too.
like control systems, sensors, actuators, like robotics design. I basically know that part. I don't know much about the bio part. I only took one course in biology, but I'll learn as I go on. So anything to do with circuitry and mechanics, I can literally I got this year's bio.
These guys never
Yeah, so I actually built one with this is not for school, this is just what I did a couple years ago. It's a control system based project I just did by myself because I wanted to show the companies what I can do. You can actually balance. The balancing is horrible, it sucks. It doesn't work at all. But you can actually control it with a PS2 controller. So like sensors and actuators. So it picks up sensors from the air and it can walk. It's still bad because it always falls over on its face. So imagine a robot that just falls over on its face. And instead of telling it to like stand up, it just walks every time you tell it to walk. It just doesn't. But I like done stuff like this a lot. I do have some knowledge on it.
Can anybody check if you have access to the Google spreadsheet? I think some of you sent me some requests, but I put the whole class in there. So can you quickly check if you have? I should see some of you popping up here. Yeah, I see some. I see Maria. Thank you.
My research project.
So much. There is a group chat that people might share within, and I want to see if I can sneak him over there. Because I feel like that might be good. Because if so, I can ask around these dragons too. And then, even though if I can I can actually ask around who can I meet up with. But unfortunately, you're under. You're not sure. Yes. There's 60 of us here.
I'll do a scoop. I gotta do one. Are you gonna wear other?
Oops.
It's a good thing. If I just straighten my hair, it would be good. Every time I go to the barber, she's like, she like does this shit. She really cool people. She uses and I just like.
If we do meet up again,
Rock climbing.
I might be here next week, but I do want to start on projects, I guess, with either something like whoever I'm going to talk to. But there is a movie. Is there a water fountain?
Yeah.
I'll go.
It's like I gotta tongue that stage. Yeah, the jersey's so fun. It's just a suit. So like, why not? I guess. He like works from home, so he's just on the 2 hours. You know that fucking meme of that crowd singing "Please Let Me Go"? I can't stop thinking about This is what they did in the Coliseum. They flooded that shit. They have boat battles there. We're bringing it back.
Okay. All right, guys. Let's spend the last half an hour or so, just a little bit more today to go through the introduction part before we get started with more the course content. Okay. As I said at the start, listing the BioMEMS applications is not an easy job because there's more and more applications opening up every single day, almost, to be honest. Because then you start thinking about, the devices and the technologies that you have available, and then it's much easier to say I can build a device for this application, but I can also use the similar process to build a device for another application. Okay, so that's why designing is such a fundamental component in this process, because then you realize that once you have the design processes, you have a solid understanding about the design process and the tools, then the application doesn't really matter. Okay, you just need to design it to be compatible with that application. Okay, so that's a powerful aspect of BioMEMS. Okay, and that's how we usually start the design. We start from the ground up, and then we develop technologies and processes that finally translate into a specific device. For talking, I'll ask you if you're either you're sitting, otherwise just step out. It's easy. Otherwise you'll interrupt a little bit the flow there. Thanks. So diagnostic tools is number one application. Okay, historically, BioMEMS come from microelectronics devices. So if you ever open your phone, you see a lot of microelectronics devices in there. These were invented in the 50s. Okay. And alongside with these devices were all the technologies that we use to build these devices, okay? So MEMS is a technology that kind of piggybacked on top of microelectronics and say, hey, you've got cool devices, cool tools there. We can use them to do something different. For example, we can develop a diagnostic tool for example. A microfluidic diagnostic tool where I have cells that flow through a channel, and then I can measure them, I can analyze them, I can do all sorts of things. We don't need to only use this technology to develop microchips for microelectronics for mobile phones or computers. But the technology is exactly the same. So microelectronics and MEMS are cousins, okay? The only difference is the mechanical part, okay? So microelectronics are purely electronics, okay? So electrons flowing through the device. Here we have mechanical components. So we can actually do manipulations, cell manipulations. We can do drug deliveries and things like this. But historically, diagnostic tools was the very first application that people thought about. Hey, I can run diagnostics on a Petri dish, but with some functionality added. Okay, I can have a macrosensor there that I didn't have before. So Petri dish was based on just microscopes. Okay, I was actually looking at what was happening in the cell culture. Now I can sense as well from the same microplate. Okay, these are the kind of applications. And this turns into personalized treatments, drug delivery devices, tissue engineering, how to build tissue scaffolding. Okay, so you actually create an environment where cells can grow naturally, because cells grow in 3 dimensions. They don't go on a flat surface inside us. They grow in 3 dimensions. So can you use MEMS to actually develop scaffolding where cells actually, combine and organize in a proper network? Then you can understand a lot more about cell cultures than you would with a flat and planar device. Minimal invasive procedures. Okay, so I won't go through all this in details. It's just for you to have an understanding about the different applications. And again, you can pick from some of these. You can pick from the list. You can combine different applications. But there's a lot going on. Okay, so we talked about DNA sequencing, patient-specific medicine. This is a huge field of research that probably some of you are somehow dealing with or studying or working on projects on. You take stem cells from patient, you differentiate them in whatever cells you need, and then you put them back into the patient. It could be cancer therapy, could be tissue growth, for example, could be organs, for example, and drug discovery, specific drugs that work for that patient, that don't work for other patients. But MEMS come into this equation as far as the differentiation process is concerned, because the differentiation process is quite critical. Okay, you take stem cells, you want all those stem cells in the stem culture to become neural cells. But it's not going to happen, okay? Because maybe there's something in the differentiation process that actually doesn't happen very much. So you end up with a lot of alien cells within the cell culture. So you don't have that culture that you want to use for, okay? So MEMS come into play because we can actually devise or design a Petri dish that has some actuation that translates into cues to the stem cell differentiate. For example, if I'm growing cardiac cells, I want them to beat, right? But if I'm growing kidney cells, I don't want them to beat. If I'm growing cardiac cells, then I could have actually some actuators that send cues to stem cells, and that's exactly how it's done in research. You have little actuator that can be just a membrane that says, you're going to be a cardiac cell. You have to learn to beat as soon as possible, okay? And if you don't want to beat, you're not going to be in this cell culture, okay? So that's the kind of stuff that BioMEMS is actually used for in these kind of applications. Drug delivery systems, we see a range of these kind of systems. The microneedles approach actually comes from a silicon-based approach, okay? So silicon wafer, you do these little microneedle cones, basically, that are minimally invasive, so you can actually have a patch. You can push the patch into the skin. It breaks just about, because these are like sub-micrometers in size, so you won't even feel it. And then by diffusion, you can let the drug diffuse. This is back 20 years ago. what people are doing now is pressure control, because I don't want too much drug, I don't want too little drug. So I can have an actuator that actually controls the pressure and the drug delivery, the drug disposal, based on what? On information from, I don't know, glucose levels or something like that. Okay? So that's the kind of systems that we are looking at right now. Control loop, closed loop systems, where I'm sensing something, glucose is going too high, inject a little bit of drug, wait, but not too much, because otherwise the glucose will go too low, and you know, it starts oscillating. The system starts oscillating. Okay. Minimal invasive procedure, catheter based. MEMS is having a lot of impact in catheter based. Usually a catheter is just a big cable that you insert in the body to reach certain specific deep regions of the body, maybe intravenous. Okay, so you go all the way from, for example, from the hip to the heart. Okay, and maybe you have to unblock an artery or a vein in the capillary system. But right now we are making those catheters a little more intelligent. Maybe I can do something else. Maybe I can do some imaging. Maybe I can do some actuation. Maybe I can do some sampling while I'm down there. Okay, so instead of having two different surgeries or two different invasive surgeries, within the same surgery I can do a couple of different things. Okay, and then the whole field of injectable, insertable devices and swallowable capsules is a very interesting field, because swallowable capsules were invented in 1954. Okay, so we're talking about 70 plus years ago. Okay, to measure temperature and pressure and pH in the gastrointestinal tract. Okay, so this is a very old technology, and then at some point someone thought, hey, we can put a camera in there and have an endoscope that is injectable. So instead of having a catheter with a camera, I can just inject a capsule, and the doctor can see in real time the image of my GI tract with a wireless capsule. And then people started thinking, why only a camera? We can measure other things. But what are the implications? So this is I have to say that swallowable capsule is usually a very popular project in this course. But you have to think about, yes, you can have a capsule with everything. But again, as I mentioned earlier, think about fabrication, think about integration. So the functionality is related to how well you fabricate and integrate these components. So you can come up with, say, yeah, I have a camera with AI, and I have a range of 100 sensors down there that measure everything, and biosensors and actuators, the sample. Yeah, okay, slow down, because all that already is a nightmare to put together. Okay, and that's why it took 75 years to get to a point where we actually have commercial capsules from 1999 from Medtronic. Okay, Given Imaging was a company that made the first camera-based capsule, but it took 50 years to get there. Okay, because we need to understand what are the key challenges when going inside the human body. Okay, it's not just like fixing a car. You see here, I have some of those papers. Okay, so you can use them, and this is fairly recent. Yeah.
You say there were long delays between the advent of these technologies and their use. Is that because of research and technology coming out, or is that due to like policymakers and regulation?
Both. Absolutely both. As soon as you get close to a human body, you got crazy regulations. Okay, FDA approvals take on average 18 months for a medical device, and you have to do a sequence of trials, starting from preclinical trials, so petri dish based. Say, okay, this is not toxic to cells. Is it toxic to animals? We're still working on animals, unfortunately, but it's one of the critical steps. And they say, it's not toxic to animals. Okay, let's move to a subsample of patients that have a specific condition. Is it toxic to them, first of all? Because that's a lot of times that happens, and then you have lawsuits that even slow down even more that. And some patients sometimes die because of toxicity of some materials that are used, the leak. Okay, you have lead, for example. Some of the materials that we're going to use have lead. We're going to see have lead. So suddenly, if there's a leak, the patient may be affected, severely affected, then there's a lawsuit. The company has to stop any clinical trials, clear the lawsuit if they do, pay trillions, and then go back to say, oh, do we have enough money to go on with the clinical trials? And there's the money involved as well. But usually, until it's proven that it's safe and efficient or efficacious for the patient, until then, cannot be a commercial product. Okay?
So do you think when our tissue and animal models of the work become more synthetic, do you think that policy will become less of a rate-limiting step?
You still have the clinical trials on patients. Yeah, I think the animal component, animal-based component, or we'll see the organs on chip. We're going to touch on that topic. Okay, so now we are trying to reproduce some of the functionality of small animals or humans on a chip. So you have heart on a chip, lung on a chip, organs on chips, okay, body on a chip, okay. That's a lot of research going on there. Still, it's a small component, and financially small compared to clinical trials. Clinical trials are millions of dollars or tens of millions of dollars, and you need enough patients. So usually you need at least, like statistical significance, we're talking about hundreds of patients, if not thousands of patients, across different regions, across different population backgrounds and all that, and ages and stuff like that. So that's really the bottleneck of this kind of technology. That's why you see an explosion of wearable devices, because wearable device class 1 regulations are limited. Does it burn my skin? Doesn't? Okay, I can wear it. That's pretty much it, right? Now there's also dispute because I can read my oxygenation level through this. This is a Garmin, okay? My oxygenation, according to the oxygenation levels, I should be in the hospital right now, okay? 92%. Oops. I feel okay, so it shouldn't be the case. But that's, accuracy. Now, if you want to call this is not a medical device, but if you have an Apple. That's a medical device now. That's a medical device. It detects arrhythmias. So you can go to your doctor and say, my medical device, but that is a different level of regulations because you can't have a patient carry a medical device that hasn't been approved to be used as a medical device. I can go to my doctor and say, look, my oxygenation level is low. The doctor is going to laugh at me. But with the Apple, they cannot now because they say, I have a medical device. It's FDA approved. So that's a kind of, system that we are navigating with this application. Yeah.
Sort of unrelated, but is the midterm and final online or in person?
In person.
In person.
Yeah. I'll make a note of all the midterms. Yeah. Midterm and final. Okay. Any questions? Anyways, go through the topics, go through the applications, start kind of brainstorming on what are you interested in, what is kind of drawing your attention when it comes to medical applications, and I posted assignments. Of course, assignments are not graded or anything like that. They're just for there for you to as a guidance. Okay. So the first assignment, I think, introduction to biomems. It's like a little bit of a brainstorming. So when you sit with your group, at least you know where to start from. You don't, apart from exchanging names and phone numbers, but where do you start from, okay? So that assignments plus this lecture should give you a starting point where you think, okay, where are you? And don't think like, sometimes it happens that one student comes to me and says, oh, my group wants to do this and I wanted to do that. And it's like, find the common ground. There's so much going on in this field. It's not clear cut. If you want to do microsensor sensing something, maybe you can integrate a sensor and maybe that becomes the novelty, okay? So don't think in a box. We are doing drug delivery system and we don't want to hear about ECG monitoring, okay? So you can't do ECG monitoring if you're doing drug delivery system. Why? Why not? Maybe there is an opportunity there, okay? And you're not graded on the novelty of the device, you're graded on how you work together, how you use the material of the course to show me that your understanding can potentially go beyond, the course, and you could potentially, design these kind of things. Again, I'll go fairly quickly. we'll start next week with microfabrication. We make a distinction between hard and soft based on the material we're using. Silicon, glass, historically, silicon is the material that all your microchips in your phones are made of. Okay, there's 90% is silicon. Okay, so that's the starting point for us. Okay, because MEMS are derived from silicon processing. Okay, and a lot of silicon processing applies to glass as well. So silicon and glass, apart from optical transparency, silicon and glass are very similar. So some of the processes are directly transferable. So if you have a process to work to design a device in silicon, a lot of the times you can just transfer it to glass. Okay, plus minus. Soft fabrication is based on polymer. Okay. So you need to synthesize the polymer, and we look at that. We start from a monomer, and then we polymerize the monomer into a chain of monomers that is a polymer, and then different chemistry gives us different polymers. Different polymers have different characteristics in terms of strength, in terms of stretchability, in terms of flexibility, and all that. Do I need one? Is it one fits all? No, it's not. It depends if I'm interfacing with a bone. For example, if I have a hip replacement and I want to have a sensor on my hip, which is a bone or a strong structure, then I don't need that flexibility that I need if I want a patch that has to be in my eye or my heart. Okay, so a contact lens cannot be made with silicon-based material. You have to be, thinking about flexible materials and so on. And also optical transparency and chemical thermal properties and things like this. So we'll go through all that. And as I said, we look at, again, I talk about polymers, but also biopolymers. So can I use cells to design a MEMS device? Can I actually use human cells to design a device? And people are looking at that kind of stuff. Okay? So we'll look at this. We'll start from this next week. What does it mean to do microfabrication, silicon-based microfabrication? We take a disc of silicon, and as I said before, we start actually, carving layers of structural layers on top of it. Okay, and we use photolithography and micromachining. It's a combination of depositing some material, patterning that material, and etching away the parts of the material that I don't need. Then I redo the process for the next layer. I deposit the material, pattern it, etch away, and then I construct my 3D structure based on that. Okay. Once I have the device, I need to test it, I need to package it. I may have two different devices that do two different things. I want to put them together so they have a fully working system. So we need to look into system integration and all that. And as I said, soft fabrication, polymer-based. We'll take a good look at hydrogels because this is like a huge research field, completely biocompatible. 90% is water, but you can make them very smart. You can make an hydrogel. If you synthesize it with certain components, you can make hydrogels responsive to pH, temperature, or other stimuli. Okay, so I can actually have a bidirectional interaction with a piece of polymer that is basically made of water. So it's actually opening up amazing opportunities. One of which is electronic skin, for example, and we'll see some examples of that. So suddenly you're going to be able to see your WhatsApp messages on your skin, right? So that's some of the things that actually happen in the, like they're shown in the news, are these kind of technologies where you integrate OLEDs, like a monitor on an hydrogel patch, and then you actually apply to your skin, and it's wirelessly connected. I am not sure we need that. I'm more focused on the bio aspect, but that shows you the kind of technology that we are dealing with. Soft lithography is a completely different process from hard micro machining. We use completely different tools, and soft lithography is a fraction of the cost, and it's something that doesn't require really very clean lab, because we're usually dealing with hundreds of micrometers. So it's the upper end of the micro scale, okay, that we're dealing with. But we'll see a lot of different processes and a lot of different materials, one of which is PDMS, which is one of the most common materials. This is something that you really need only a couple of tools that you can buy almost on Amazon, and you can actually have your PDMS substrate done in a few hours. Okay. Let me play this video. Microfluidics is another topic. There is an entire course in microfluidics, but I think it runs only a graduate level, I think, with Scott Tsai, that goes really deep into the physics, okay, and fluidics of things. We're going to keep it at a manageable level, but it's such a huge topic, and the industry is actually looking a lot at this for drug delivery, for drug synthesis, for cell analysis. They're actually incorporating more and more microfluidic chips in their processes. So I think it's a very good example of what we can do in this field. And it starts from a piece of glass, for example, and then you carve a channel in that piece of glass, and then you have a microfluidics. It's called microfluidics because the fluidic dynamics, the dynamics of the flow are different, and they don't it doesn't follow the same rules at a micro scale as it does at the macro scale. There's no gravity or things like this, okay? So we're talking a completely different scale where the flow is actually linear, and we see a lot of that. But you can use it for droplet-based generation, where you actually maybe use droplets. So this is actually a droplet generator, okay? So it's a microfluidic that generates a large number of droplets per minute, okay? Very high throughput. This is where the industry is. The industry is interested in large scale, high throughput, okay? Let's do a lot of things very quickly. That's where the industry is. That's where the money is right now, okay? So it's not enough to give them something that works well. You have to give them something that works fast and does a lot of things in a short period of time. Okay, so droplet-based, I'm not an expert of droplet-based microfluidics, but I can appreciate the applications. For example, in drug discovery, instead of having a petri dish, you can actually incubate cells within a droplet. Okay, so you can have a droplet, you can have cells incubated in that droplet, and then you can have a drug disposed inside that droplet, so that droplet becomes an incubator. Now, if you remember how this video started, or you can see from now, look at how many droplets you can have. So you can have a lot of incubators at the same time, so you can do really high throughput drug discovery with a system that is really low cost. Okay, so that's where basically, 1,000 droplets per. This is a company, okay, Elveflow is a French company that they do this, okay? So you can actually look them up. There's a lot more information. Microreactors, I call the incubator, but that's what I meant, microreactor. And actually that's what they're gonna show. Some of the application, cosmetic creams and lotions, okay? And nanoparticles, diagnostic tests and assays. Mayonnaise, if you are into mayonnaise and low-fat foods, you can use that. This is the beauty of biomed. It's like, how do you come up with these kind of applications? It's very useful. Single cell screening using dual microvalves. Okay, this is 2020, so only a few years ago. That's how they use screen of different microspheres using hydraulic pressure. Okay, they have two different channels with running at two different pressures, and they can control. And you can see the microparticle. I hope you can. No, you probably cannot see very much from here. But I posted the videos, so they are on YouTube, so you can take a look. But you can see the microsphere flowing through the channel, and then it's trapped by pressure in the by the first valve, and then it's released. Can you see that? And it's trapped by the second valve. Okay, that's the kind of stuff that you can do. But of course, you need things to be linear. So that's why you need micro channels. Okay, otherwise things are going to be turbulent. Okay, if it's a large scale, like a hose or a pump or a tube, I cannot do this kind of stuff, of course, because the flow is turbulent. I cannot control it. Okay. Lab on a chip, organs on chip, huge application range, particularly in the field of micro analytical systems. So you have a lot of different components integrated on the same system, and you can do a lot of different things. And we look at one specific component that we're all familiar with right now, which is PCRs. Okay, I think everyone here had a PCR in the last couple of years. A PCR is a sequence of analytical steps. Okay, can you integrate that sequence on the same chip without manual intervention, without having to take the sample, do something else, heat it up, and then put it back in the chip? Yes, we can do that. So we'll see PCRs, and the same applies to lab on a chip for cell analysis. You may want to do some cell manipulation. For example, you want to do some cell sorting. I don't want to analyze the whole blood. I want to analyze only the plasma. So I have to differentiate. I have to divide blood, the components of white cell, red cell, and plasma. Okay, so that's the first thing that I need to do before I actually do the analysis. Can I do that on the same chip? Yes, we can. Okay. Lung on a chip is you can look it up. This is already almost 15 years old. Very simple, but again, emulating the properties of oxygen exchange in our lungs, in our two chambers. So that's very interesting. How do you replicate that? And of course, you are losing a lot of, what's actually happening inside our lungs at this scale with a very simple chip, but it's a starting point. Okay. Microsensor, biosensors, wearable sensors, minimally invasive sensors. We look at the principles of sensors, and we look at how they are used for different applications. And we look at thermal, not radiation, thermal, mechanical, flow, magnetic, electrical, electrochemical, and so on. This is a company, actually, micro actuators and drug delivery systems. So that's where you put, you store some drug in a reservoir, and then you release it when you need it. So it doesn't get released by diffusion passively. You can control, okay? And you can have several different drugs in the same system and release only the one you need, okay? So that's the kind of the kind of applications that pharmaceutical companies are looking at. And this is an actual company where they build a reservoir, and you can see the drug in the little reservoirs, individual reservoirs, and then they have a very thin layer of gold that dissolves at a higher temperature. Okay, that layer of gold, which is biocompatible, it can dissolve in our body, no problem with that. It dissolves, and then it opens up the reservoir, and the drug starts flowing into the system. Then we look at biosensors. We look at in details a different type of biosensors, focusing on the biological element and transducer combination. We're not going to look at down the line what's happening in the front end, how you pick up the signal, what you do with the signal. We're going to focus on how do we make a sensor work as a biosensor. Okay, so what do we need to do? And there's so many different ways and pros and cons. This is a nice, I think, review paper. Microfluidics, integrated biosensors. We are already taking two topics and put them and putting them together. We have a microfluidics. Why not having a biosensor? As the cells flow through the channel, I can have a biosensor with a biological entity or element that basically captures the cell or whatever biomolecule is flowing, and I can get a recognition phenomenon. Okay. The last thing we're going to see is system integration. Okay. So once you have all these components, more often than not, as I said, you don't develop all the components using the same processes. Okay, so you need separate processes, separate materials. If you can do everything using one process, one material, that's great, but it's not going to happen. I can already tell you. Okay, so usually you get the best of each process and each technology, and then the bottleneck is how do you put this together? Because polymer and silicon, they're not best friends. I can already tell you that, okay? So maybe you have to actually have an intermediate layer where you take a polymer-based device, the silicon-based device, and somehow you make them work together. There cannot be leakage or anything like that, particularly if it's inside a human body. You cannot have a leakage in the device. So it has to be properly insulated, properly biocompatible and all that. And think, what is the surgical intervention that you need? Okay, so to implant something like this, which is a common, not this, but it's a common medical device, like a pacemaker. They make an incision, but there's only a few places in the body where I can implant this, okay? So if I make it smaller, then opens up new opportunities, okay? So I can use catheters to actually inject it, or even needles, okay? So injectable, but that means how do I make that package so small, particularly if I use several different components, okay? There you see how do you find a balance between the functionality, the size, the cost, the complexity, and all that. That's what your project is about, nothing else, okay? Not the $1 million future device. If you can design that, that's great, but the point is, how do you put all this together in a functional device that makes sense, that is, something that could be useful? Okay, I'll leave it there. And we can stop here. And as I said, I suggest you to go through this with your groups, like in the coming weeks, couple of weeks. Sit together, start forming groups, and then start sitting on some of these questions. Okay, what are the advantages and disadvantages of miniaturization, design consideration, limitations, and all that. Okay, so try to start putting a story together before week 4. Okay, so I'll see you next Friday.